All right, we are now on lesson 8.3, logarithms and logarithmic functions. Okay, and within this section, we're going to have two learning targets that you can define and evaluate logarithms or simplify logarithms. And then the other thing is that you're going to be able to use the inverse properties of logarithms and exponential functions. Okay, and then that one will kind of come as we go throughout the rest of this chapter. Okay, so let's actually define a logarithm. So one thing that we want to think about is, well, we can determine that like 2 to the second power is 4, or that like 2 to the third power is 3, because 2 times 2 is 4, and 2 times 2 times 2 is 8. But what about when we're trying to evaluate like 2 to the x power is 6? So you need to think about like, well, what number can I multiply 2 by itself and get 6? Well, that doesn't have a nice, neat answers, but this is exactly where logarithms are going to be used. So this is going to be used to solve problems where we have an x variable in the exponent, or we're trying to find parts like that. Okay, so let's let b and y be positive real numbers, but b can't be equal to 1. And the logarithm of y with base b is denoted by log base b of y. Okay, so we have logarithm base b of y is equal to x if and only if b to the x power is equal to y. So b to the x power is equal to y. And so what this is going to help us find is this is going to help us find different parts of an equation like this. And oftentimes it's most helpful when we can find the variable in the exponent. Okay, so log base b of y is equal to x if and only if b to the x power is equal to y. Okay, so let's go ahead and just kind of rewrite some logarithms in kind of the most basic form, and then that will allow us to find or just to understand them more. Okay, so let's go ahead and take a look at this one. So this first example here, when I'm rewriting in logarithmic form into exponential form, we're looking at this log base 2 of 16 is 4. Okay, so this is saying that when the base is 2, I have to raise 2 to the 4th power to get 16, is what this is saying. I have to raise 2 to the 4th power to get 16. Okay, so log base b of y is equal to x. So we can use this same form here. If we need to, we can even write it down. Log base b of y is equal to x. So what's in the x or b position is 2 to this 4th power is 16. So to put it, 2 to the 4th power is equal to 16. Okay, and so then this one's saying when I raise 4 to the 0 power, I get 1. When I raise 4 to the 0 power, I get 1. Okay, so 4 to the 0 power is equal to 1. Okay, next one. Oh, actually, that's about it for this particular section, so let's go ahead, pause the video, and try the next two on your own, just trying to rewrite them in exponential form. Okay, so when I have this here, this means I'm trying to raise this little 12 here as our base to the 1st power, and that's going to be equal to 12. Okay, when I have log base 1/4 of 4 is equal to -1, this means when I raise 1/4 to the -1st power, I'm going to get a 4. Okay, so this relationship that between logarithmic form and exponential form is one that you're really going to need to know. So when we start using the inverse properties to actually solve for little problems here, that's what's going to be most helpful to us. Okay, and so then this relationship here continues forward. Okay, so now I'm in exponential form. I want to write it in logarithmic form. Okay, so we need to think my base here is 5, my exponent here is 2, and that's 25. So when I'm looking at this, I know that my base is 5. So I'm going to say when I take logarithm of with a base of 5 and I raise it to what power to get 25, I'm going to raise it to what power. So basically this is the question. When I write this in, like if I were to type this into my calculator, log base 5 of 25, essentially would be saying, what power do I need to raise 5 to get 25? And we know that that is 2. Also because of this x here, or this exponent here is a 2 as well. All right. So what about the next one? So the next one, we know our base is 6. So when I have a log base 6, okay, and then my result here is 1 over 216. Okay, and again, what is this asking? This is asking when I take 6 to what power, this is going to give me what the exponent's going to be. Is going to be 1 over 216, and then that one is negative 3. Okay, so essentially if I were to get rid of this equal sign with the numbers here, these are just trying to find out what exponent does the base need to be raised to get this number. All right, so why don't you pause the video right now and go ahead and try the next one. Okay, so I'm assuming you already paused your video and you're moving forward here. So the next one here, my base here is 10. Okay, and when I have my base 10, my result is 1 over 10, and I want to know what power do I need to raise 10 to get a result of 1 over 10, and then that is negative 1. Okay, next one. I guess that this is also an important, when your base is 10, you actually can just write log, and whenever you have log there, it's implied that the base is 10. So if you don't write a base, it's implied that the base is 10. Okay, so let's do the next one. Okay, so log, and what's my base here? So you all should be hopefully telling yourself that the base is 8. And when I'm done with my base of 8, I'm getting a 4. So I need to think about what power do I need to raise 8 to get 4. And that is 2/3. Alrighty. Okay, so hopefully we've recognized the relationship between an exponential function and then a logarithm or logarithmic representation between the two. Okay, so now let's actually evaluate some logarithms here. Okay, so now when I'm looking at these, okay, I need to think about what the base is and what my result is. So essentially, the question that I'm asking myself here is when I have a base of 4 and I'm getting to the 64th power, I want to know what, or not the 64th power, but when I have 4 as my base, the 64 is telling me that's the result I'm getting. I need to figure out what is that exponent there going to be raised to get 64. Okay, so if I take 4 to the second power, that's going to give me 16. But if I go 4 to the third power, that's 64. Okay, so 4 to the third power is 64. So that means log base 4 of 64 is just equal to 3, because that's the exponent here that would make this true. Okay, so here it might be important to know that 0.2 is also the same, 0.2 is the same as a fifth. All right, so again, when we're looking at this here, we want to know what power do I have to raise 5 to get 1/5. Okay, so we may have noticed that the number has gotten smaller. In fact, it's a fraction that involves a 5. Okay, and so we need to think about, like, what would this exponent need to be to make this expression here true? What power do I need to raise 5 to get a result of 1/5? And then that's -1. Okay, and this is going to require that you know some of those exponent properties that we worked on in, I believe it to be chapter 6 pretty extensively. Okay, 7. Okay, so what power do I need to raise 1/5 to get 125? Okay, so I know that this is a fraction, but when my exponent is negative, I reciprocate this fraction. I flip it upside down. So this is going to be pretty helpful in knowing that, well, I kind of already know here that I'm going to have a negative exponent because I'm going from like fraction to whole number, and this one's like whole number to fraction. Whenever you kind of have that pattern here, you're going to end up with a -1, or a negative, not -1, but a negative exponent. So what you need to think about is like, okay, so I know that I'm going to have a negative, and that's going to kind of flip this fraction around to give me a whole number. Now I just have to think about what exponent is going to get 5 to 125. Well, if I had exponent 2, that would get me 25. So exponent 3 is going to give me 125. So this exponent here is -3. And you could check any of these problems here. Like if I wanted to check number 7 here, I could just go ahead and I could take my 1/5 and I could raise it to the -3rd power, and it's going to give me 125. Okay, so if you're not strong with some of your exponent numbers, it is going to be a little bit of a guess and check, but not entirely. Okay, so here, number 8. Here I know I'm going to have a base of 36. Okay, to what power is going to be equal to 6? Well, hopefully you've recognized the relationship between 36 and 6, and that 6 squared is 36, or the square root of 36 is 6. Okay, so when we look at this problem here, I know that they have that special square root perfect square relationship between the two, and so that's going to indicate to me that, you know, I'm going to have to think about what exponent represents square root. Okay, in chapter 6, we talked about what number can I raise another to a power that represents the square root. Okay, so we need to know that the square root of a number, okay, is the 1/2 exponent. Okay, and again, I can go ahead and check this, and I can take 36 and I can raise it to the 1/2 power. Okay, and I'm going to get 6. All right. What I want you to do is I want you to go ahead and pause the video, and then I would like you to try some of these on your own. Okay, so I'm assuming that you've already paused the video, all right, and you've tried some of these, okay? So E is just asking, like, what power do I have to raise 4 to get 256, okay? You may not know this number right off the bat, but, you know, this doesn't hurt just to go ahead and play with the numbers a little bit. So 4 to the 2nd power, I know is 16, so it's going to be more than that, so let's try 3. So 4 to the 3rd power is 64. Well, that's not going to work. Okay, let's go to 4, and that's 256. So this expression is equal to 4. Okay, next one, 0.125. Okay, now this is a decimal. It might be helpful to know that 0.125 is the same as 1/8. Okay, now, let's say you did not know that. I've shown you this before. You can take any fraction, hit math, frac, and it will tell you what fraction equivalency it is equal to. All right, so we know that we're trying to figure out base of 8 to what power is going to be equal to 1/8. Okay, so as we talked about before, we have a little bit of reciprocal nature, right? We're turning number into fraction here, specifically with like some common base power 8. Okay, that means I'm going to have a negative exponent. Okay, my negative exponent here, well, what power does 8 need to be raised to get 8? Well, that's just 1. Okay, so 8 to the -1 power is 1/8. Okay, G. Okay, I want to know the relationship between a base of 1/3 to some power is going to give me 27. Okay, what power does 1/3 need to be raised to get 27? Well, think. Okay, again, we have this reciprocal relationship between fraction to whole number, so we probably are indicating that this is going to be a negative exponent. Okay, now I just need to think about what does 3 need to be raised to get to 27. Well, 3 to the second power will get me to 9. 3 to the third power will get me to 27. So this is -3. All right. Okay, and then lastly, here I have base 64 to some power is equal to 8. Okay, and again, hopefully we've identified the relationship between 64 and 8. Okay, 64 and 8 have a square root and perfect square relationship between each other. 64 is the perfect square of 8, and 8 is the square root of 64. So we need to know what number as an exponent represents square root. And that is, again, 1/2. Okay, if it had a relationship between cube and cube root, you would use a third. If it's fourth and fourth root, it would be a fourth, so on and so forth. Okay, so let's go ahead and move on to the next page. So let's just go ahead and talk. And we talked about this a moment ago. Had I read further, I might have kept that to myself, but I did not. Okay, so a common logarithm is a logarithm with base 10 and is denoted by log base 10 or just simply log. So essentially, anytime you see just log, okay, we're assuming that the base is the number 10. So what number would I have to raise 10 to get another certain number? Okay, there is another one, and this one is going to be the natural logarithm, and the natural logarithm is with base e, and it can be denoted by log base e, but I can be honest, I've hardly ever seen that, and it is almost always going to be denoted by ln. Okay, so if your base is e, it's going to be denoted with ln, and we've already talked about e in 8.2. Okay, so if I have two functions, log base b of x and f is b to the x power, those are inverse functions. This is the power of logarithms, natural logarithms, common logarithms, is they help us solve problems where our unknown part is going to be involved in the exponent. Okay, so they're going to be extremely powerful in solving each other. Okay, so what I can do here when I'm looking at this very first problem is I have 10 to the power of log base 10 of 4. Okay, so here's the nice part is like log base 10 and taking to the 10 power, they kind of undo each other. And by kind of, I mean they undo each other. Okay, they're inverse operations of each other. So if I have like a log base 10 and a 10 as a base here, those kind of reciprocate, or not reciprocate, they undo each other. They're inverse operations. So the only thing that's left over here is just a 4. Okay, so that's just kind of the relationship, right? So if we take, if we look at this one, if I have this base here is the same as the base in this log, whatever I'm taking the logarithm of is just going to be that number because they're inverses of each other and they undo each other. Okay, so now let's look at this one. This next one is a little bit more unique, okay? Because, based on 9, you would think that we're looking at the relationship between the log base and the base here. And I need to figure out what this x value is. Okay, well, even though they're not the same base, the bases are very, very similar to each other, right? 5 and 25 do have a very unique relationship to each other. So what if I rewrite this? Log base 5, and then I'm going to say this is, put this in parentheses. 25 is the same as 5 squared. Okay, so all I did here was I replaced 25 with something that it's equal to, but involves a base of 5, such as 5 squared. 25 is the same as 5 squared. Okay, so here I have this relationship here, okay, where, okay, this is log base 5 of 5 to the 2x power now, right? Exponent properties tell me that power is the power I multiply. Okay. And then when I simplify, I know that log base 5 and then an actual base of 5 here are going to undo each other. So the only thing that's left over is whatever's in this exponent here. And this is just 2x. Okay. Pause the video, move on to the next section, and see how you do. Okay. Here on I see that I have a base of 8, and then in my exponent, I have a log base 8 of x. Log base 8 of x. So I know a log base 8 and an actual base of 8 undo each other. And so the only thing that's going to be left over is whatever the of the logarithm is. And so that is just x. Okay. J. Okay, so here I have log base 2 of 64. Now 64 very well could be a power of 2, so we should probably check. So I think 2 to the 6th power is 64. So I'm going to rewrite 64 as 2 to the 6th power, and then that to the x power. I'm rewriting 64 as 2 to the 6th. Okay, which means that this is log base 2 of 2 to the 6x. And again, a base of 2 and a log base 2 are inverses of each other, and they're going to undo each other. So what's going to be left over here is just 6x. Okay, so this is the inverse relationship between an exponential function and a logarithmic base function. Okay. What we're going to do from here actually is this is the end of this particular lesson, and this is just the beginning of the inverse relationship between the exponential functions and logarithms. Okay, and as we move forward, what we're going to do is we are going to actually start to solve some problems here and use some properties of logarithms. Ultimately is kind of where we're leaning towards. So again, today, looking back at our learning targets, we needed to be able to evaluate logarithms. Okay, so as I evaluate logarithms, we're looking at ones where there's no equal sign and it's just like log base 4 of 64. We have to figure out what that exponent would be. It also says we need to understand some relationship between inverse properties of logarithms, okay? And that's what these ones are going to look like. Understand that having a 10 as a base in your logarithm and as like your standard base in an exponent are inverses of each other and undo each other. They cancel each other out, just like adding 5 and subtracting 5 would do as well. Otherwise, that is it. Move on to the homework, and I'll see you for the next lesson.